All right, hello. Welcome back to the 2.7 part 2 video. We're going to be talking about just a few more things having to do with molecular geometries, dipole moments, and bond hybridization. Okay, so let me skip back down here through these slides. Okay, so dipole moments. All right, so you should recall that covalent bonds between atoms can be either polar or nonpolar, right? H2O is a great example of a molecule that has polar covalent bonds because the difference in electronegativity between hydrogen and oxygen is fairly large, and so we end up with a partially negative charge on the oxygen atom and partially positive charges on the hydrogen atoms. Okay, now the question that we're going to be asking ourselves when we talk about dipole moments is, does having polar covalent bonds make the molecule itself polar? Is having a polar covalent bond enough to make the molecule itself polar? And so in order to answer this, we have to investigate the geometry of the structure. Okay? In the case of water, it does. All right? So let's look at why. Okay. So when polar covalent bonds are present and there is asymmetry to the structure, some sort of asymmetry, then an overall dipole moment is present. And in these cases, we would call these polar molecules. All right, so what do I mean by asymmetry? Certainly there is some symmetry here in H2S, okay? Like if I draw a line down the middle here, like a vertical line, there is definitely some symmetry there, but there's also asymmetry present, okay? If I draw a horizontal line, right, this north end, or the top end of the molecule, is going to be partially positively charged, and the bottom end is going to be partially negatively charged, right? So that's kind of the asymmetry that you're looking for. You want to be able to sort of draw a line and say, okay, this end of the molecule is going to be positively charged, this end of the molecule is going to be negatively charged. Same thing happens in ammonia, okay? NH3. You end up with a partially negative end on the nitrogen and then partially positive ends on the hydrogen end. It's important, though, to understand the 3D molecular geometries that are at play here. Okay, let's look at H2S. All right, if H2S was linear, okay, if it was linear, then I wouldn't have been able to draw that line of asymmetry, right? Same thing goes for ammonia. If ammonia had been trigonal planar, I would not be able to draw that line of symmetry, okay, or asymmetry. This is what I'm talking about, okay? If you have a situation where the molecular geometry doesn't have asymmetry, okay, if symmetry is completely present, like if everything is symmetrical, then even if you have polar covalent bonds, you're not going to observe an overall dipole moment. What effectively happens is that the bond polarities kind of cancel each other out, and you end up with a non-polar molecule. Okay, so these are some good examples of this. Carbon dioxide. Even though the carbon-oxygen bond is a polar covalent bond, the fact that you've got well, first of all, you've got the perfect symmetry, right? You can't really draw lines of asymmetry here. Horizontally and vertically, things are symmetrical. What happens is when these molecules are around each other, there's not really an observed overall dipole moment. What I mean is there's not really an observed negative and positive end, right? You see how like this end would be negative, this end would be negative? What that means is that just sort of overall, when these molecules are with each other, they don't really observe like a positive and negative end. Okay, and that's really what we're going to be getting into at the beginning of Unit 3 is intermolecular forces, having positive and negative charges on different atoms that are attracted to each other, or on different molecules, keeping them sort of bonded together, like hydrogen bonding, if you learned about that in biology. So, long story short, okay, if the molecule is sort of completely symmetrical, right, if you have sort of this linear shape or this trigonal planar shape, or in the case of methane, a tetrahedral shape, you're going to be, even if you have polar covalent bonds, you're going to have a non-polar molecule, okay? You need some sort of asymmetry, so like a bent shape, a trigonal pyramidal shape, or just a diatomic molecule like this. You need some sort of asymmetry in order to have an observed dipole moment. Net positive and negative charges on the molecule, okay? All right, I did want to take a moment to go through and look at the simulations here just to give you guys a really good idea of this. So here's water, H2O. This is definitely asymmetrical, right? Especially if I don't show the lone pairs there, right? You can see how this is asymmetrical. But if I look at something like CO2, for example, okay, this is nice and symmetrical, okay? So even though the carbon-oxygen bond is polar, the net overall polarity here is not present, okay? Like I said, the bond polarities effectively cancel each other out. They're sort of both pulling in opposite directions, and so the net polarity here is 0. The same thing applies for a tetrahedral shape, like with methane, okay? And granted, methane is, these bonds aren't superpolar in the first place, okay? The difference in electronegativity here is only 0.4, so this wouldn't be considered very polar at all anyways, but the fact that it's got this tetrahedral symmetric shape means that it's going to be non-polar. And then just to give you one more example, let's look for like a trigonal planar scenario here. This would also be a geometry that is perfectly symmetrical. There's not going to be any sort of dipole moment here, whereas in ammonia, you do have that asymmetry, right? You can have sort of a negative end on the top and the positive end on the bottom. Okay, so it's the fact that we've got this lone pair here that enables ammonia to be polar, whereas with this molecule, there are no lone pairs, trigonal planar, perfectly symmetrical, no net dipole moment, okay? All right. The next thing that I need to talk about, and this topic is really complicated, so we're not going to get too deep into it, but we're going to talk a little bit about bond hybridization, okay? So once again, we really only need to know a few things, so we're not going to get super into the weeds on this, but I do want to, there is potential that you may see some questions about this on the AP exam, so we'll get into it here. All right, so covalent bonds are shared electrons, right? That's what a covalent bond is. It's shared electrons that are in between two nuclei, in between two atoms, right? So where exactly are those shared electrons, okay? And that's what this whole concept of bond hybridization is going to be answering. Where are the shared electrons that are involved in covalent bonds? So electrons in a lone atom exist in orbitals, right? And we know this, like 1s, 2p, 3d. These are the orbitals that exist in a single atom. If you were just looking at one atom by itself, that's where the electrons would be. Shared electrons between two atoms exist in what are called hybrid orbitals, okay? So basically what happens is the orbitals from the two bonding atoms hybridize or overlap to form these hybridized or alternatively shaped orbitals, okay? Once again, it has to do with like the minimizing of energy. That's where the original electron orbitals come from in the first place. So like I said, the details involved in this are really, really complicated, so we're only going to focus on a few key concepts. The names and types of these hybrid orbitals, which you do need to know, the resulting bond angles, which you kind of already know, and the concept of sigma versus a pi bond. Okay, this isn't actually that complicated, so we'll get there in just a second. All right, so first of all, the names and types of hybrid orbitals. Basically, there's 3 types of hybrid orbitals, okay, that are going to be assessed on the AP exam, potentially, all right? There's sp orbitals, sp2 orbitals, and sp3 orbitals. These 3 cases occur depending on the number of effective pairs around the central atom, okay? So 2 effective pairs, sp hybridization, would be a case, let's see, can I get that simulation back up here? So 2 effective pairs would be a case like this, okay, CO2, where there's no lone pairs, okay, but I have 2 bonding partners here around my central atom. Okay, so the carbon in this case would be sp hybridized. Okay, that's how this is referred to, sp hybridized. What that means is that the bonding pairs here are in sp orbitals. Rather than being in s orbitals or p orbitals, they're in a hybrid, an sp, okay? And once again, the details behind this are super complex, so I don't need you to know much more other than this. If there are two effective pairs around the central atom, that's going to be sp hybridized, okay, and that's going to be a linear shape, which has 180-degree bond angles. Okay, this part you already sort of knew, right? You could have determined that carbon dioxide with its two effective pairs would be linear shape. Okay, the next case is when you have three effective pairs. This is called sp2 hybridization. An example of this would be BF3. Okay, so having three effective pairs. Okay, there's no lone pairs here. Okay, so we have 1, 2, 3 bonding partners here. Those are my three effective pairs. And so the bond hybridization that's involved here is just called sp2. Okay, and that results in a trigonal planar scenario shape with 120-degree bond angles. Okay, and then the last one that you need to be aware of is when you have four effective pairs. This is the tetrahedral shape. Okay, that's called sp3 hybridization, or sp3 hybridized. So once again, that's the tetrahedral shape, and that results in 109.5-degree bond angles. I do not think that it is required for you to understand how these orbitals form, or really much more than just the fact that they exist. Okay, so this is almost something that you kind of want to be memorizing. I know I'm not a big fan of memorization, but this is something that you really just sort of want to remember the details of, not necessarily applying it to a ton of different problem solving. One other thing that I do want to mention is that with sp3 hybridization or sp2, these effective pairs, these can be like bonding partners, or they can be lone pairs. Okay, so if we look at water, for example, okay, this would be a case of sp3 hybridization because there are four effective pairs. There's the two hydrogens and then the two lone pairs. Okay, so this would be this would not be sp hybridized. Remember, sp is always going to result in a linear situation. sp3 is always going to result in a tetrahedral shape, right? And remember, this is tetrahedral in terms of the electron geometry. The molecular geometry is just bent, right, because those are the only atoms that we see, but the overall shape is tetrahedral. All right, so this would still be that sp3 hybridization, not sp. Okay? Here's a few just images that I wanted to show you. This sort of shows you the orbitals that you start with, the process of hybridization. So this is why they're called like sp versus sp2 versus sp3. In sp hybridization, you're making hybrid orbitals, or like alternatively shaped orbitals, out of the s and p orbitals. Okay, and so you can kind of see how the linear, trigonal planar, and tetrahedral arrangements arise. Okay. Also, here's another example of one molecule that has a lone pair. That lone pair occupies that orbital, right? So like if I look at my ammonia case here, this is just another example of sp3 hybridization. Even though there's only 3 hydrogens, there's 4 total effective pairs around the central atom. So this is just another example of that case of sp3 hybridization, the tetrahedral shape, even though there's only 3 atoms there connected to the central atom. Okay, moving on. All right, the last thing that we need to talk about in this video is the concept of a sigma bond versus a pi bond. Okay, so sigma bonds, these are Greek letters for sigma and pi. Sigma bonds are the first bonds to form between bonding atoms. These bonds exist as direct overlap of orbitals. Okay, so you can see here between 2 carbon atoms, the sigma bond would be the single bond here, where you have sort of 1 electron here, 1 electron here. There's those up and down arrows that we were using in the electron orbital diagrams. The 2 electrons would sort of reside here in this overlap. Okay, that's referred to as a sigma bond. Okay, pi bonds are only going to be there if you have a double or triple bond. okay? So if you have a single bond between carbons, it's always going to be a sigma bond. If you have a single bond between carbons, it's always going to be a sigma bond, okay? And those two electrons are going to exist in this overlap. If you have a double bond, then you're going to have one sigma bond, but then you're also going to need to use a pi bond. Pi bonds exist as an indirect overlap in the space above or below, if you think of it two-dimensionally, above or below the sigma bond, okay? Once again, these details are really complicated, okay? So I don't need you to necessarily know everything there is to know about sigma and pi bonds. Here's what you really do need to know, okay? Single bonds will always be sigma bonds, okay? So the first bond that forms between two atoms, whether that's carbon and carbon or carbon and oxygen or oxygen and oxygen, the single bond is always going to be a sigma bond, okay? So there's going to be some direct overlap and the electrons are going to be directly between the nuclei. If you have a double bond, okay, say a carbon-carbon double bond, this is always going to consist of one sigma bond and one pi bond. And then if you have a triple bond, this is going to consist of one sigma bond and then two pi bonds. So it's like you start with the sigma bond, and then if you happen to have a double bond, you're going to tack on a pi bond, and then if you happen to have a triple bond, you're going to tack on another pi bond. Okay, so that sigma bond is always going to be there. Okay, sigma bonds are the strongest of these two types. Okay, sigma bonds are stronger than pi bonds, and you can actually sort of observe that in this table. Okay, look at the bond energy of the carbon-carbon single bond, 347. Okay, kilojoules per mole. Now, when you double the bond, right, go from single to double, the addition of that pi bond, it's not as strong as the sigma bond. How do I know? Look at the bond energies, right? A sigma bond between carbons has a bond energy of 347. Now, if I were to double that value, right, to go to a double bond, this would be close to 700, right? 350 times 2 would be 700. So this bond energy should be close to 700 if pi bonds and sigma bonds were equal in strength, but they're not, okay? Pi bonds they're not a direct overlap. They're sort of like this indirect tangential overlap where the electrons sort of exist here in this space, but it's not as nice of a scenario as a sigma bond, okay? Not as energetically favorable of a scenario as a sigma bond. So the pi bonds aren't as strong. They're easier to break than single bonds, okay? And you can observe that here. And then as you go from the double to triple, the difference in these energy values is even less than it was here. So like the third bond or the second pi bond that's added here is even less in energy, is even weaker than the first pi bond or the sigma bond, okay? So just to review, okay, because these concepts are sort of all over the place and there's a lot going on. For the sigma and pi bonds, what I need you to know is that sigma bonds always form first, and they're the strongest of the two types. Okay, pi bonds will only be present if you have double or triple bonds, and they're weaker than sigma bonds. Okay, as long as you can remember that, that should be okay. All right. Okay, well that's it for this video. I will see you guys in class on Wednesday. Okay, no class on Tuesday because of election day. Right? Okay, thanks for watching.